Okay, everybody. So we're going to switch topics a little bit. We're going to talk about, once you built your agent-based model, what do you do with it, right? How do you use it for a scientific paper? How do you publish it? How do you write up your results, right? And I'm going to use a different example. I like to use lots of different examples so that you see lots of different models, right? And this is kind of similar to the information diffusion model, but it's different. We're going to talk about spread of disease between people, right? So if a disease infects 5 people before the original person recovers, becomes non-contagious, right? Then in 3 steps in the infection, the disease will actually infect 156 people. That's pretty fast growth. On the other hand, diseases have a natural tailing off point, which is just how many people there are in that area, right? So they eventually reach a capacity constraint, right? And that's a resource limit, right? And when we model disease, often we do it using what's called the SIR models, right? Which are these standard models that say the probability of you getting a disease is equal to whatever, right? And then once you become infected, the probability of you recovering at each time step is a different number, right? And we're just going to model the system dynamics in that way, right? Now, there's a problem with those models, right? Which is, first of all, they don't tend to take into account that there really is no such as uniform mixing, right? The probability of me interacting with all of you is much different than the probability of, say, me interacting with Donald Trump, right? And so there is no uniform mixing of everyone in the population, right? The other thing is that different people have different susceptibilities to disease, right? Some people are more likely to get a disease than other people are, right? And there's environmental interactions that can occur. And so all these things are things that we can model using agent-based modeling to better build models of disease. So we have a model called the spread of disease model that's built into the NetLogo examples. Wow, I think I just killed my NetLogo. So give me a second. It's usually pretty robust, but every now and then I do weird things with it where I have like 15 versions of it running and stuff like that. So here's our spread of disease model, right? And let's look at the mobile version first. And so what you're going to see is that there's a couple of people who are infected with the disease. They're red, right? And there's 3 people actually. And they're going to run around at any time they touch a person, actually on the same patch as a person who doesn't have the disease, they're going to give it to them, right? And so you can see how quickly this disease spreads. And as you can see, you see what we talked about. Fast takeoff, but then a resource capacity, right? The disease ran out of people to infect, and so it dies off, right? So that's the simplest version of the model. Now, why am I introducing this model? I'm introducing this model because we're going to try and use this model to actually look at some scientific results. So what if we want to know how population density affects the spread of disease, right? So we have a mobile model, right, where people run around. So the closer people are together, the quicker the disease should spread, right? But let's try and understand that a little bit. So here's a model. Here's a run that they did, where in the first run, they ran it with a population of 50, and it took 419 time steps to get to 100% disease. And the second run, and they also did 100, and it took 108, 150 took 169, and 200 took 127, right? But in the second run, they got slightly different results, where 150 actually took less than 200, right? So a natural question you might ask is, how do we know what the actual relationship is between the disease spread, the population density, and the quick spreading of the disease, right? Is the second run more the correct one, or is the first run more the correct one? Maybe we need to do some more runs, right? So we do a lot of runs, right? And one of the ways we can analyze the data or start to think about the data is to look at all the raw data. So here we're looking at all 10 runs, right? And we can look at that, but that doesn't really help us very much. It's hard for any person to understand what's in that data, right? What's going on there very easily. So we can start to do things like analyze the data in other ways, right? We can start to look at means and standard deviations. We can start to look at graphs. So that's what I'm going to talk about in the next few minutes, right, today, is how to analyze this data in different ways, right? So first of all, the point I want to hammer home, and I mentioned this in the very first class, is since almost every single model that you're going to build in an agent-based model is going to be stochastic. Even if it's not stochastic in the decision making, it's going to be stochastic in the initial conditions. You need to make sure you do multiple runs, right? There are different ways to do that in NetLogo as there are in any agent-based platform. One thing you could do is you could just literally write code in NetLogo to run the model multiple times. Right? So I can write this code in NetLogo and just run it. Let's see, actually save it somewhere. Yeah. So you'll see I have some code. It's called my experiment. And all it does is just repeat 10 times, set number of people to 50, run the setup. While not all turtles infected, go print ticks, right? So let's talk about what that does, right? Set num people to 50. So this is something you haven't seen before, but you can actually, in the code, change a slider, right? So I'm actually setting the slider in the code, right? And then I'm going to run the full setup routine. And while, as you probably all know, means while something is true, do this code, right? So while not all turtles are infected, right? So all turtles are infected. When that's true, so that's going to be false as long as one turtle is not infected. And as soon as all of them are going to be infected, it's going to become true, which means the not is going to make it false, which means we'll exit the loop, right? So we're going to just do go, and then we're just going to print ticks because we know that we ended immediately after it all, right? So we can run this code. It's going to be kind of slow at first, so let's speed it up a little bit. And there we go. And we got the results, right? And you're never probably going to run your models this way, right? But I want to show you that like anything we're doing with any fancier experimental tools is just something you could do in the actual code, right? That's the point I want to make. We're not doing anything tricky when we run these models the other way later on, right? Yeah, exactly. That's what I want to make. That's the exact point I want to make, right? This is exactly what behavior space is doing for you. It's just automating it for you. But the reason why I want to make that important is sometimes people think behavior space is doing something special or different. It's not, right? It's just running NetLogo code for you, right? But just in a specific set of circumstances. So, as you point out, this is what behavior space is doing for us. So we could set up behavior space to do the same thing, right? So let's set up a behavior space experiment that does exactly this. In fact, I have one built in here that does it. So we'll pull it up. And this is the most important part. Right here, it says set the number of people to 50 and then increment it by 50 until you get to 200. Repeat that 10 times, right, for each of the different values. The output measure is ticks, just because it has code built in that stops when everyone gets infected. So all we want to know is how many ticks have gone by. And we don't even need to measure runs at every step. We just want to know the final numbers, right? So we can run this. And by the way, I always like table output over spreadsheet output. The difference is the table output is going to put it all as rows in a table. Spreadsheet output is going to put it all as columns, right? And it completed already. It's super quick once you turn off the display, right? So now I can actually just double click on this file if you have like anything that reads a CSV. For me, it's going to pop up Excel, but it, pop up whatever CSV editor you have built into your system. And now I can see the results. Hopefully. Excel is always really slow on Macs, so it takes a while. There it is. Okay. So as you can see, it has what Behavior Space does. It gives you a little header, which is kind of nice, which just tells you what model you were running, what version of NetLogo you ran it on, so you know that, what experiment you were running in that model, when you ran it, the dimensions of the world, right? And then each row is a run followed by all the parameters of the model, followed by your output that you asked for, right? And in fact, I could have put no output because one of the things that automatically outputs is the step, right? So the outputs that array. You'll notice that they're out of order, right, by the way? And the reason why that is because when I'm running the model, as I mentioned earlier, it's running it 8 times, but I'm only seeing 1. So it just outputs them as soon as it finishes one of the runs, right? If you want to see them in order, you can just sort by that column, right? And you'll get them all in order, right? But so now I could take this data, and one quick thing I could do once I sort it appropriately, so I can sort it. Right? I can then take the values for each of the numbers and average them. Right? So I can say equals average. Right? And that'll be the average of all the ones where the population density is 50. And I can copy that down here to 100, 150, and 200, right? And now I have something that's a little easier to understand, right? I have 10 runs averaged for how long it takes to get to 100% infection, right? And my cursor's kind of blocking the one. So you can see that it goes, and I'll blow that up too. Maybe 150. You see that when the population density is 50, it takes longer, and then it goes lower and lower, right? And if I want, right, I can even start to graph this data like I would any kind of data to look at the results, right? So I can, and I can also compute things like the standard deviation, right? So I could take this code, move it over here, and then just change this to standard deviation. Is that what it is? No. I always forget what it is, and I think it misses one of the D's. There we go. Oh, how is that possible? Hold on. Oh, I changed the columns too. That's right. Okay. Okay. So that's another one of my pet peeves, by the way. I hate agent-based modelers who publish graphs, who put graphs in only the averages without the standard deviations, right? First pet peeve that gets you like an automatic reject is putting in anything that's just like one run and here's our results. I hate it when people do that. Second one that gives you an almost automatic reject is that you don't put any error bars on your graphs, right? Which people do a lot of, right? But anyways, so now I could take this data and I could build a graph with both means and standard deviations, right? So there's the raw data, summary statistics, easy to do in R as well if you want to load it in there. Creating graph, easy to do in R. You can also do it in Excel. In the interest of not showing off my terrible Excel skills, I won't build the actual graph, but I have done it in the past. It's possible to do. And if you have any questions about that, I also want to spend some time talking about other models we haven't gotten a chance to talk about to give you some other examples. So, here's my graph in R, right? So this is, darn it. This is a graph in R where I actually I just graphed all the data, right? I kind of think this is a useful graph when you have a small amount of data, right? Or even if you had, and a lot of times, even if there's concentrated data, it's useful to do it this way, right? Here's the graph with the standard deviation bars built into it, right? So now you can see the results between them, right? And it looks pretty. One of the things I like about doing like one standard deviation or one standard deviation in this case is that the difference in means test is just whether that bar overlaps with that bar, right? So you can kind of quickly eyeball if there's statistically significant difference between some of these points. And there's not between this point and this point, and there's not between this point and this point, and there's not between this point and this point, but it looks like there is between this point and this point, and this point and this point, for instance, right? Of course, you want to do the statistical test to confirm. But. Yep. Why do you think it does? You don't know? You don't have a guess? Does anyone have a guess why the standard deviation goes down? Yeah? What? A larger number of data points, yeah. What is that what you're saying? Yeah? Yeah. Yeah. Yeah, well, think about it, right? We're plotting time to 100% infection, right? When there's only 50 points, 50 agents, they kind of be scattered all over the place. And if you happen to have a situation where they're all scattered very far from each other, it's going to take a lot longer than if you happen to start in a world where they're all close to each other. When you have a higher density, it's harder for that to happen, right? It's harder to have this situation. So yeah, the number of data points is the same, but the probability of it happening within the same system goes down, right? Yeah. Yeah. So I could do that. Actually, if I wanted, it's real simple. And in fact, I think I have an example of it coming up, but I'll show you real quick. So if I go back into that, if I click in measure of runs at every step, this button, right? And I hit run, table output. Go ahead and replace it, that's fine. Oh, cancel. Actually, just want to delete. No, don't save that. So now I have both of these. I'm probably going to want to do it because it's still going to write out every time it completes a tick. It's going to write out to the file. So now they're way out of order. So what I want to do when I sort is I'm going to first sort on run number, and then I'm going to also sort on tick, right, or step, yeah. And now they'll be exactly ordered, right, in the order I want. Now, in this particular case, I'm not outputting anything interesting. I'm only outputting ticks, but yeah. Can you record a video of it? Yep, there's a great example. I won't show you completely, but there's a code example in NetLogo. Discard. So there's movie recording example, and it'll show you how to do it. Essentially what it does, and we'll go ahead and open it. I don't need to. Essentially what it does, it actually has an extension called video recorder that it calls. So I haven't talked about this yet because this is like what I was going to wrap up with at some point. But NetLogo has both what they call an extensions API, which allows you to write code in Java, or basically in Java, and then call it from NetLogo, right? Now, because Java has hooks into like Python and everything else, you could actually write the code in whatever you want, right? And then call it from NetLogo. But it also has what's called a controlling API, and the controlling API allows NetLogo to be controlled from Java, right? So I can have a Java program that calls NetLogo code, right? And the extensions API is often used for these reasons, right? For things like, for more advanced code, right? It's not built in. You actually have to write code to do it, but it kind of works. Okay. Oh, so, by the way, these are one standard deviation, right? Error bars. Technically, that's not really what we want because we actually have multiple runs computing each of those things. What we actually want to do in a lot of statistics is do a standard error, which is to take our standard deviation and divide by the square root of the number of runs that we have, right? So then we calculate a standard error. Those are a lot better. So under this kind of a calculation, all the data points are maybe statistically, this last two, maybe not, but I'd have to do the maths to figure it out. Okay. So these were all end of the run results, right? They weren't results over time. And so this is exactly the question you were asking, right? So runtime graphs are often useful to look at, but they require lots of data and they kind of become hard to understand, right? So here I have all the plots of all the runs of the number of people infected at every time step, right? And you can I always like to look at these graphs first in this way because I find it very useful. Like, when we do means and standard deviations, we're assuming that the data is normally distributed, right? And it may not be, right? And what I mean by that is you can imagine, what if in half the runs of 200 people it goes like this, and half the runs it goes like that, right? Just because of something in the model, right? Like maybe there's a big wall down the middle and some people don't make it over the wall or something like that, right? Then we should understand that. And if we do the means and the standard deviations of the runs, what we would see is just something halfway between the two. But that's not telling us the whole story, right? That's only telling us part of the story. So I always start by plotting all the data, right? Because I want to kind of understand, is it okay for me to make the assumption that the data is normally distributed, right? Now, if I was even smarter, there's a whole bunch of tests you can run to verify that the data is normally distributed that exist in statistics, right? But usually, for the purposes of most of the type of research we're doing, we don't need to do that. We can just kind of eyeball it and say, yeah, it's roughly normally distributed. I'll now run, I'll do the analysis the way I want it to. So then we can start to graph it like this. So in this particular case, I'm graphing the number of infected over time with an error bar on each of those time steps, right? And so this really starts to let me understand at what point are the runs different from each other, right? So the beginnings look all the same. The ends obviously look kind of similar to each other, right? But the time along is when we see some differences between the runs, right? Okay, so let's talk about other things you might want to analyze in this model. So let's imagine we want to throw an environmental variant into this model. So now, the disease is like the common cold, where the cells actually exist outside the body for a limited amount of time, right? This is why they tell you, when you leave the bathroom, for instance, right, you're supposed to use your elbows or something somehow to use the door so you don't get the germs that are there on the doorknob, right? So let's imagine a disease like that, And now we can plot that disease instead. So this is built in. And you can kind of see what happens there, right? And in this model, there is this disease decay. And that's after that space becomes infected with disease, how long the disease stays in there, right? So that's one of the controlling characteristics. So we can ask the question, let's keep the number of people constant, but instead control the disease decay and see how much the environmental effect has on the system. And so one thing you could ask is you could be comparing different diseases, some of which have a faster disease decay than others, or you could be comparing how important is it for us to clean the bathrooms every hour, right? Versus every day or something like that, right? That would be another way you could be assessing the impact of this effect, right? It's one way to think of it. So we can pull up the model, behavior space. There's a model called environmental. As you can see, there's the 0, 1 to 110. We can run this model. It runs pretty quickly. Again. And so, by the way, one thing I like about this is something often the way I build models, I'm building an extension to the model, right? I have this basic model, and let's imagine I've convinced a group of reviewers that basic model is a good model, right? Now I want to add an extension. I just don't throw the environmental in there. I added something that was important. I added a disease decay of 0, which basically turns off the environmental effect, right? It says that there is no, the disease decays immediately, right? And so as a result of that, what that allows me to do is create some results that are in the model without the environmental case and some that aren't. So now I can show the difference between those two setups. I always think whenever you're building your models and you're adding additional complexity to it, you should always make it so there's some parameter that allows you to go back to the first model. And anytime you do that, it's really nice because it means your original model is a sub-model of your bigger model, right? And it allows people to kind of compare and contrast. Otherwise, they're somewhat qualitatively different models, right? And that becomes harder to compare and contrast between the results. So I can graph this data after I pull it in. And rather than taking you through all the R code, I'll just do it here. If anyone's interested, I do have all the scripts saved for how to do this, so I'm happy to share them with you. Maybe I'll put those on the local drive as well to make it easy to access. And you can see how the different effects have. So obviously, as the environmental decay increases, right, the time to 100% infection goes way down, right? So what this seems to say is that even for moderate rates of environmental decay, we get a quick infection, right? So essentially, we either need to, if we think about this from the how often should we clean the bathrooms problem, we either need to be cleaning them all the time, or we should just not worry about it, right? Because it doesn't really matter, right? One of the two is what this says. I don't know if this is realistic. I haven't really validated against any real data. It's purely theoretical, so take all that with a grain of salt, right? But that's the basic idea. We can also do the kind of mean and standard deviation trick to kind of simplify the data and make it a little more obvious. And now we can start to take it to another level, right? We can start to think about a network variant. So as we mentioned, this previous model, that model assumes that if me and Donald Trump are in the same model, we're just as likely to run into each other as me and, my wife, right? So that's obviously not the case. So instead, we can build a network version where, me and Donald Trump are on the opposite ends of the network from each other, and maybe it's 20 degrees of separation between us, right? And so in that case, we can start to look at how those things affect the overall spread of disease. So we're going to run a network model where we control the density of the network. So you see, we look at how many connections per node we have, starting at 1/2, and that might seem weird, but it's a stochastic network, so 1/2 means that on average every 2 people has 1 connection, but because a connection has 2 ends to it, that means on average every person has 1 connection, right? Does that make sense? It's a little tricky, right? Because we're going to generate connections so that everyone has 1/2 has a probability of 50% of having a connection, but once we generate that connection, that actually means that everybody is on average supposed to have 1 connection. They may not. There may be unconnected nodes in the network. Now, the other thing you'll notice about this model is we can't run it to full infection. We have to give it a time limit of 50. Why do we have to give it a time limit of 50? What are you going to say? What is that? Yeah, it could run forever because of unconnected people in the network, right? So as a result of that, we want to limit this. And this is something, if you know your model may not stop, or even if you're not sure if it's going to stop, I recommend putting a time limit in, right? Because otherwise it'll just keep going and going and going, right? So we're going to put a time limit of 50. How do we come up with 50? Well, we actually played with the model a couple of times, and we saw that roughly we got to the maximum completion around that time period. If you're going to do this scientifically, you might want to say we ran it for 50, 100, 150, 200, and the results were robust to changes in this value, right? But in this particular case, we're just going to set it at 50 and go, right? So just to see it, because you haven't seen this model yet, there it is running, right? And so there are a lot of unconnected people at 0.5, as you can imagine, right? Actually, I must have explained that wrong. I think that in this case, the probability of anyone having a connection eventually is 1/2. It's not that everyone it winds up with 1 link. That was a misstep. I'll have to look to see how we do the code. Might have actually even changed since the last time I built this model. So in this case, right, it's not going to, that was it. Because, so this is interesting. This happens a lot of times. That was 80 runs, but the one in the foreground took so long to complete that it completed all 79 in the background while the one in the foreground was completing, actually. So this happens occasionally. And that's partially because the network visualizations are very computationally intensive, right? By the way, they float away like that because we're using a network layout algorithm called the spring layout algorithm. And in the spring layout algorithm, the assumption is that any 2 nodes in the network are connected and have to have a link to each other, are connected by a spring. And the spring pulls them together, but the nodes themselves repulse each other, right? And so as a result, any nodes in the network are repulsed from each other. The nodes around the outside aren't connected to anything, so they actually don't play a role in the overall spring layout algorithm. Does that kind of make sense at a high level, right? It's a little bit of an artifice of the way spring layout works, but it's kind of cool because it kind of makes them look like they're floating around, right, a little bit, so. So once we have that network version, we can do things like graph infected after 50 steps. So this graph looks different, right, than any of the other graphs we've seen. Even as high as an average degree of 3, we get 0 people infected after 50, or not 0, but a low number of infected after 50 steps. Why do you think that is? You're on the right path, right? But this is 1 person getting infected. Yep, exactly right. So you can have 1 person who is completely isolated from the rest of the network, right? Even at an average degree of 3. Because we're choosing the initial seed randomly, right? If we wanted to modify it to make sure that we always had at least a decent number, we could choose an individual in the giant component, right, and infect them, right? But in this case, we chose them randomly. And so as a result, we get these kind of crazy results, right? Anytime I see something like this, probably means I need to run my model for longer time steps, right? Or thinking about how to address the fact that I had those zeros, right? And figure out maybe I need to infect more than one person, right? Or something like that at the initial time steps, right? Because those standard deviation bars are way too big, right? Compared to the ones around them. So far, we've constantly been talking about how to just analyze one data point, one output, right? But a lot of times in an agent-based model, there might be multiple variables that we want to look at together, right? Up until 2 dimensions of output with 1 dimension of performance, 2 dimensions of input with 1 dimension of output, I did say that right. Up until 2 dimensions of input with 1 dimensional output, we can actually visualize this. After that, we can't, because as far as I know, no one has the ability to visualize 4 dimensions right now, right? So, and if any of you do, let me know. That'd be cool. But we can do that. So, what we can do, but there are other ways we can do that. One solution we can also do, let's say there's 5 input dimensions we want, right? We could run the model with all 5 dimensions, and if there's some natural base value, right? Like everything turned off, for instance, right? We can just graph the differences from that base value, right? That's one solution we could have, right? Another solution we could have, and this is something that's an interesting approach that people have talked about, agent-based models are complex systems, right? So if there's a bunch of input things that are going to change or could change in the real world, right, then just aggregate over everything, right? Vary all of your inputs and average the output over all of them, right? And that kind of tells you roughly what the expected range of all possible outputs is, right? And I've done a couple of models like that, and it kind of makes sense. It's a little weird, right? Because you're kind of comparing some apples to oranges when you change some of those input parameters. But if there are things that could happen in the real world, I think it makes sense. If there are things that are artificially changed, right? Like the social network structure, right? Then that seems odd, right? But if you're just not sure, right, if the susceptibility to disease is 0.5 or 0.7, right, and it can go anywhere in there, and you're not sure if the average degree density is 3 or 4, right, and you're not sure if the disease lingers in the environment for 1 hour or 2 hours, throw all that in, average, and what you're going to get is kind of the upper and lower limits, right? You could look at the minimum values coming out and the maximum values out, and that kind of gives you a robustness space. It tells you how robust the results are to the inputs, right? So that's something that you don't see a lot, but actually I think it has some worth, and I don't think people explore it very often. Then you can use 3D charts of combinations. That's what I was mentioning. You can, as long as you have 2 inputs and 1 output, you can do that. And you can do regression, right? And regression is kind of the final thing. We can essentially treat the model as an experiment and regress an output on our inputs. And that tells us the relationship between those inputs and our outputs, right? So in the model we're going to look at density of the population and this environmental decay aspect. Wait, hold on, let me show it to you real quick. So as you can see, this is the first time I've shown you a behavior space model where we're changing 2 parameters. So we set disease decay to go from 0 to 10 by increments of 1, and number of people from 50 to 200 by increment of 50. Repetitions is 10. Can anyone, oh, well, it kind of says it right here, so I won't ask this question. But I was going to ask the question, how many runs is it going to take, right? Well, it's going to be the full combinatoric, right? So this is 11 values. This is 4 values. 4 times 11 is 44, times 10 runs, 440 runs. Does that make sense? So, by the way, the one thing behavior space doesn't let you do, right? The behavior space always does the full combinatoric. So let's imagine that I wanted to run 50 people with values from 0 to 5, 100 with values from 2 to 7, and 200 with values from 7 to 10. I can't do that easily in behavior space, right? Just so you know, the easiest way to do it is actually to just build pieces of code that set the parameters for you, right? So I can have a code that says condition 1, right? And have that be one of the pieces of code. Condition 2, condition 3, right? And those conditions would probably be setting the disease decay correctly or something like that based upon where I was in that space. Other thing you do, if you got the computational effort and it's not going to take too long, just run the full combinatoric and throw away the combinations you don't want, right? That's the other solution. It all depends upon whether the computer time is too costly. Okay. So once I run that version, right, you can see it going on. Right, so this one's going to take a little longer to run, and you can see it kind of went through a non-spatial and a spatial version of it, but it eventually completed. And then, as I mentioned, you can look at base cases and variance. So in this case, I basically am looking at if I fix number of people at 100, how does environmental decay affect time to 100% infection, right? And in this case, I'm fixing disease decay at 5 and altering number of people, right? And I can show, 4 graphs of this and 4 graphs of that, or whatever you want to show the relationships between them, right? I can also just aggregate. So this is just averaging over all of them, right? So this is the case I was mentioning, right? And as you can see, standard error bars go way higher in those. Why is that? Any ideas? So I'm averaging over all the number of people and all the number of decays. And if you look at it, the decay bars are much higher. Sorry, the standard deviation bars. I apologize. It's a decay. Yeah, because we're averaging over more things, right? And those things are more different from each other, right? And so as a result, it's going to drive up my standard deviations. So this is kind of, as I mentioned, it's kind of showing you the kind of outline of the space of routes that the simulation could take, right, through that space. Then I can do a 3D plot. This is one I did in R, right? And so I can kind of plot number of people on one axis, average decay on the other. Time to 100% infection is on the z-axis. And as you can see, actually, I should reverse this coloring, right? Because blue means that everyone gets affected right away, and red means it takes forever to everyone to get infected, right? So probably we want blue and we hate red, but just in the interest of plotting, that's the way it wound up. And finally, I can do a regression. So I can literally just put this into a regression where I regress the time to 100% infection on the number of people, the disease decay, and an interaction term between the two inputs, right? And as you can see, the only thing that actually shows up as being statistically significant in that is the number of people, right? And that kind of makes sense when you look at a lot of these error bars, right? Because a lot of these error bars up here, the disease decay winds up being very non-significant once you get over 0. And statistical models aren't very good at teasing out the fact that there's like one value where it might be statistically significant and the rest are non-statistically significant, right? Now, I could recode that if I saw this pattern and I wanted to make that argument through a regression, I could just recode my input parameter as 0 or non-0, right? And now run the regression, and almost certainly disease decay would now show up as being statistically significant, right? But because when we do a regression, we kind of average over all these values, right? None of those are statistically significantly different from each other. And so the regression line is going to kind of go right through the middle of them and not really be different from 0. Does that make sense? Yeah, okay. So this is a cool idea, and I don't think people do this often enough, by the way. I don't think people a lot of people publish their agent-based models, and they do it like this, right? And the problem with doing it like that is just that it's really hard to say holistically what the effect of the inputs is on the outputs, right? Now, it does let you tease out certain things, right? Like if I just look at the regression, I can't notice that at values close to 0, the model is different, right? I would say, oh, there's no effect, right? But what it does say is that, what it does let me do is say that overall, that number of people variable is much more statistically important, at least, than the other things. And I can also start to look at, well, these aren't standardized inputs, so I can't really compare the estimates. But I can start to compute elasticities, right? Which is how much a change in one of these variables would affect the output variable, right? And start to think about that. So 1 unit of increase in disease decay, right, barely affects the time to 100% infection is what this says, right? But 1 unit in the average number of people seems to directly affect the time to 100% infection, right, by at least a unit, right? So I can start to compute things like that. I like this idea of mixing econometrics with agent-based modeling, but I don't see many people doing it. Yeah? Yeah. Yes, if there's a correlation between them. Of course, then you could use something like, if you have a lot of variables, you could use like lasso regression, right? Which will then helps deal with correlation. You can, of course, calculate the VIFs and do it yourself, right? But I always like lasso because it solves that for me, right? And I don't have to worry about it, right? Or elastic net or one of those kind of implementations, essentially, all right? What else I was going to say? I'm just going to bet this. I think that was it. Just that, that these are, you do have to think about what these implications are, right? So that's it for analysis of agent-based models. I hope, after we complete the tutorial today, right, what I'm hoping you've taken away from this class is how to think about a model, right? How to build that model, how to analyze the results that come out of that model, right? And, hopefully thought a little bit about like how you might actually go about designing a research enterprise that used agent-based modeling, right? Now, what I want to do to end this class from the theory perspective is I'm going to spend some time talking about where agent-based modeling came from. And that may seem like a weird way to end the class, right? Maybe I should have started it, right? But I think it's important to see all the different kind of classic models that have come along over time, right? And kind of explore some of those. Now, I am not going to be talking about like the modern state-of-the-art of agent-based modeling, like the most recent models that have come out, right? I'm happy to discuss that with you, right? And talk about that. But I had to choose between one or the other because we only have 45 minutes left, right? And I decided to talk about the history because I thought that was more important. Besides, the state of the art is really going to vary based upon your field, right? If you're interested in theoretical biology, there's a different state of the art for agent-based modeling than if you're interested in the economic and social sciences. Just to give you a quick peek into what I'm most interested in, though, right now, what I'm most interested in is the idea of combining big data with agent-based modeling, right? I want to take large data sets, infer agent-based models from those data sets automatically, like infer decision rules from those data sets, and then put those directly into an agent-based model, right? In a way that the rules that are governing the agents are interpretable, right? So that I can take those rules and I can go to theory and say, do those rules make sense from a theoretical perspective, right? That's really what I'm excited about. And I have a book chapter on that I'm happy to send to anyone who is interested in that topic. Just got published. I work a lot with our Defense Department, and this was a project with DARPA, the Defense Advanced Research Projects Agency, and RAND, who I'm not associated with. RAND actually is a corporation in the U.S. that stands for Research and Development, kind of a boring corporation name. It happens to be my last name, but we're not related. They actually published a book about the future of computational social science and agent-based modeling. And my chapter is called Theory Interpretable Modeling and Model Interpretable Theory. I want to see a world in which those two things both come together, right, in interesting ways. So that's my personal perspective. I thought I'd take 5 minutes to share that with you, and I'm happy to point you to additional research if you're interested in the methodology of ABM in that area. But that being said, I want to talk about where ABMs come from. So let's go back in time to a much simpler time. Okay. History and roots of agent-based modeling. So let me talk first about this guy. We already mentioned, yeah. Sure. Sorry, go ahead. Yep. There is no way to take the actual plots that show up in the NetLogo model. You can. There is code that will save the plot output to a file, right? So, it's a good question. Honestly, I should say this before I show you. I'm a big fan of using the best tool for the best job. NetLogo plots, not necessarily the best plots in the world, right? It's really good for just understanding what's going on in the model, so it has to be built into that. I would argue that you should probably output the data and plot them in R or Excel or Tableau or whatever you want to plot them in, right? Rather than plot them in NetLogo. That being said, you can do it, right? So one thing you can do, if you just want a quick plot just to put into a presentation, you can actually just copy the image from the plot, and you can just paste it to someplace. You can export it, right, as raw CSV data if you want, and just plot it that way. And then I believe, let me look this up. This is always, pretty sure this is true, 90% true, right? There's a way to automatically do it. So it'd probably be under plotting. Autoplot, plot access. I thought there was a way. Save. There you go. Export all plots, right? Export plot, right? These will allow you to export some of the plots directly to a file. So you could write into your code, right? So it's a little tricky, right? Because if you're running a behavior space, right, it's not necessarily updating the visualization, but you could still force it through export plot to export the plots out. I've never tried that with behavior space, right? So I don't know if it's going to work, but I think that it maintains the state of what the visualization should be. So I believe it could do it, but I haven't tried it. So you could be the first person to try it. But the other tricky part about it is that if you exported all the plots with the same file name, that's going to cause a problem. It's going to keep writing over it. So you'd have to have some way of having a parameter that you pass in that controls the file name so that you can make sure you export to different file names too. Does that make sense at all? Okay. Any other questions about NetLogo? Actually, this is a good place to, we'll have an hour and a half this afternoon to talk about NetLogo too. Okay. Let me talk about John von Neumann. So John von Neumann is my academic great-grandfather, actually. So my advisor was a guy named John Howland, so he's my father, if you will, right? His advisor was a guy named Art Burks. Art Burks, his advisor was John von Neumann, right? I got the pleasure to meet Art Burks. John von Neumann, unfortunately, passed away before I was before I became a grad student, so that wasn't possible. But Art Burks was he was retired but lived in Ann Arbor while I was still in grad school, and he would attend a lot of like retirement ceremonies and things like that at the grad school. So I got to escort him to the retirement ceremonies often because I was the closest relationship to him academically that they had at the time, right? So John von Neumann helped develop one of the first computers, the ENIAC, and he wanted to develop self-replicating machines. So you got to remember, this is like, we're talking about in the 40s and 50s, right? He had this idea already that like we should be able to use these computers to create more computers, right? That's crazy. Like, who thinks things like that? Like, I just built this cool device that can calculate, the exact orbit of a missile, right? And now I want to use it to make another thing that does the same thing. Like the jump of logic there actually kind of amazes me to this day, right? But that was what he thought of, right? And so he collaborated with this guy named Stanislaw Ulam, who is a mathematician, to develop what was known as cellular automata, right? And cellular automata are these cool, you could think of them as simplified agent-based models, right? They're agent-based models in which each of the agents is stuck in a patch, right, and can't move. And the only thing they can look at is the patches around them, right? Does that make sense? To make their decisions. And they can't really do anything except change their state. And their state is an integer, right? It's like 0, 1, 2, 3, 4, 5, right? And that's all they can do. And in fact, the most agent-based models are actually not even two-dimensional. Most cellular automata are not two-dimensional, but one-dimensional, and the agents only have two states, on or off, and they could only look at the neighbor on either side of them, the vast majority of them. Now, we can play around. There are other versions, right, out there, but that's the most. And in fact, so John von Neumann actually built a two-dimensional cellular automata, right, in which each cell space had 29 states, and he actually proved that this was a universal constructor. You essentially could feed this cellular automata instructions, and it can build anything, including another universal constructor, right? So he created the first machine that could build itself. Now, it only built itself in the memory of a computer, right? It didn't build a physical machine, but essentially it proved that once you solved the engineering problem of a machine building another machine, it was possible for machines to reproduce, right? Like, you can think of this as a proof of existence, right? That self-replicating machines could some reality. And I don't know if you've heard about it, but with some of the work on MakerBots, they're getting closer and closer to this. They're actually developing MakerBots that can make other MakerBots, right? Now, you can always, don't worry, they're not going to take over the world, because they don't have enough resources right by them to like kind of constantly be making more MakerBots. Humans have to keep feeding them resources, right? But they can kind of infinitely reproduce as long as they have access to enough resources to do so, right? So this is not too far off into the future at this point. The cool thing is he thought about it 70 years ago, right? So before it was even close to being possible. So along came a guy named John Conway, and John Conway wanted to play around with these cellular automata, right? And he was kind of intrigued by them. And he came up with this idea of something called the game of life. And the game of life is probably one of the simplest cellular automata that exist, but still has amazing amounts of diversity, right? So in the game of life, if a cell has 3 neighbors, it goes from being a 0 state, a dead state, to a 1 state, right? It has exactly 3 neighbors that are alive, right? If it has 2 or 3 neighbors, and it is alive, it stays alive, right? Any other combination results in the cell dying. And he argued that if they have a lot of neighbors, you could think of this as like a cellular model of like amoeba, right, in a petri dish, right? And if there's a lot of amoeba competing for the same food, right, the cell's going to die. If there's no cells for them, I don't even know, amoeba actually might be a bad example because they reproduce asexually. But if there's no cells around, for some reason they die off, right? They're different then. Interesting enough, this game of life, as simple as it is, can be both self-reproducing. You can create things in the game of life that reproduce themselves. Again, limited by resources, because if you set up the world, you set up with some finite boundary conditions, and they can only recreate until they run out of space, right? And this is the coolest thing about it. Turns out the game of life is what we call a universal computer, which means that any problem that you can compute in the game of life, right? So that means that theoretically, you could build Fortnite in the game of life, right? Like anything that's computable can be built into the game of life. Now, the matrix probably for building Fortnite would probably be like 1 billion by 1 trillion, right? Like it'd be a huge world. But you could theoretically write all the code of Fortnite in the game of life, right? So that's kind of a cool little finding of this, right? So the next step in this is Arthur Burks. So Arthur Burks carried on von Neumann's work, and he's, as I say, he's my academic grandfather, right? So von Neumann, just before he passed away, started working on a book called The Theory of Self-Reproducing Automata, but he hadn't finished it. And Arthur Burks was his grad student at the time, and Arthur finished it for him, essentially, right? And then published the book, right? And that was, we kind of, at that point, 1966, besides Conway's work in the game of life, we kind of hit a dead spot in cellular automata theory for a long time, right? No one was playing around with them. And then along comes this guy, Stephen Wolfram. How many of you have heard of Stephen Wolfram? Do you know what he did before publishing A New Kind of Science? Do you know what he invented? What? Mathematica, right? So he invented Mathematica, right? And then he decided on the basis of Mathematica, oh, I guess it says it up there. I should have hidden that from you. On the basis of Mathematica, partially, he decided to, but he was really a scientist, right? He basically built Mathematica to help him explore mathematical objects, right? He went on this long crusade to explore all of the possible rules for 1D cellular automata, right? And look at all of them. And in fact, he makes an interesting claim in The New Kind of Science, if any of you have read it. He says that at the basic state of the world, right, like down at the quantum level, right, things are either on or off, and they're affected most uniquely by the things just around them. So he actually argues that the world is one large cellular automata, that the universe, that everything we know, that everything that exists is a cellular automata. And he kind of makes that as a strong claim, that the world is computational. I find it interesting, and take it as you will, right? But he also did some fascinating work in this. That being said, I find his, small caveat, I find some of his stuff a little, he doesn't tend to cite where he's getting his ideas from as well as I would like. I would love for him to give more credit to where things came from, right? We actually had him give a talk at Michigan while I was there, and Arthur Burks was in the audience, and so we acknowledged Arthur Burks before his talk went on. But anyways. But nonetheless, you can't argue with the fact that Wolfram really kind of brought the idea of cellular automata to the next step. So what is the relationship between cellular automata and agent-based modeling? Most people seem to think, if they learn about these two independently of each other, think that agent-based modeling grew out of cellular automata, that one of them gave rise to the other, that people were playing around with cellular automata and were like, oh, what if the agents could move, right? And then that's where we got agent-based modeling from. In reality, when I was writing the textbook, I had the chance to talk to, I would say, about a dozen of the earliest agent-based modelers, right? People who had written the first agent-based models. I asked all of them that question. I said, did agent-based modeling grow out of cellular automata? And to the one, none of them said that it did. They all said it didn't. They said that they were aware of the cellular automata work. I mean, one of the first agent-based modelers was John Holland, my advisor. He obviously knew what his advisor had done and knew the work of cellular automata, so he was quite aware of it. But he thought of agent-based modeling as something different, right? It was something where he said, it was just one of those things where we're starting to build these economic, in his case it was an economic agent, was one of his first models. We wanted to build these economic agents, right? And we realized that the best way to do that was by building agents into a computer simulation, right? We didn't really think of that as anything to do with cellular automata. Now I see that there's a relationship between the two, but at the time that's not where it came from, right? There's no evidence then that there is a direct academic thought line that you can draw from cellular automata to agent-based modeling. Now, you can always sociologically impose that thought line after the fact, right? But as far as we know from the actual history of science, that line does not exist, right? That being said, there's a lot of results that are similar, right? Each cell can be viewed as an agent. Von Neumann's models, actually, the way von Neumann describes his cellular automata is he describes it as, imagine a creature sitting above a gray soup that can kind of pick up and put different things down, right, in that space, in this biological sense that sounds almost agent-like, right? He was talking about almost like an agent. The cellular automata have a scheduler, right, where every tick something happens, right? There's a tick and then the system changes. It's very similar to the agent-based model scheduler. Wolfram's classification, so Wolfram has this way of so what he did was he took each rule that's possible in the 1D cellular automata. He saw what the results of that rule were when you ran it in a variety of conditions, and he classified them as to whether they were, I think they were fixed, random, chaotic, or periodic, I believe is the way he classifies them, right? It turns out that's surprisingly similar to some of the modern attempts to classify complex systems, right? So there's this relationship between, and a lot of times those modern attempts to classify complex systems are using agent-based models to characterize them, right? So there's a lot of relationships there, but they're not directly related. So let me talk about, so we're going to take one more step a little forward in time. So my advisor was a guy named John Holland. Here's a picture of John Holland. Actually, I believe this is him in Beijing at the time, before the Olympics, right? He used to travel to China quite a bit towards the end of his life, right? Because he did a lot of work with educating Chinese people. He was inspired by Hebb's ideas about neurons. So Hebb has a great book wrote one of the first neurophysiology books about how neurons work. And his argument was neurons that fire together stay together, kind of, right? That the more they fire, the more they continue to activate each other, right? And Rosenblatt developed this thing called the perceptron. Have any of you ever heard of the perceptron? Some of you do have, okay. The perceptron is essentially, you know what a neural net is, or at least you've heard of a neural net, right? Imagine that we just take one kind of connection in a neural net. That's a perceptron. That actually is. All neural nets are many, many perceptrons, right? So Rosenblatt had developed this idea of a perceptron for computing simple functions, right? And Howland said, well, these are cool, all these ideas about biologically inspired computational models. What if we did the same with evolution? Right? What if we took the ideas of evolution and did it? And I know you guys have had a class on genetic algorithms already, but he decides in 1975 to publish the book Adaptation in Natural and Artificial Systems, where he describes the first genetic algorithm, right? Howland was also influenced by a guy named Samuel, who developed the first reinforcement learning algorithm to play checkers, right? And based upon that idea, he started to think about how can we take evolutionary concepts and embed them in a system that's trying to solve a problem, right? Like an agent that's trying to solve a problem. And so he starts to think about agent-based modeling, right, really. And Howland became involved in something called the Santa Fe Institute, which is probably the premier research institute on complexity, around 1985. And he actually was one of the founders and original members of that organization, right? In September of 87, they had one of the first kind of really cool meetings at the Santa Fe Institute, where they brought together economists and physicists and different thinkers, like John Howland, who is a computer scientist, to discuss the economy as a complex adaptive system, right? During that meeting, he kind of started working with Brian Arthur, Blake LeBaron, Richard Palmer, and Paul Taylor to create the first Santa Fe artificial stock market. So this was the first time that anyone actually thought about representing all the traders in a stock market as artificial agents in a system, right? And it was a really cool model where they eventually showed that they could reproduce market crashes and market busts and market booms and all this in a model that had not perfect economic agents. These were boundedly rational economic agents, right? Around the same time, in 1986, John Reed, the CEO of Citicorp, met at SFI with Ken Arrow, a famous economist, Brian Arthur, another complexity thinker, and John Howland, to think about new ways to model economics. And they started to work on the idea of what would eventually become Swarm, which was this first agent-based modeling language. It didn't exist then. It didn't come around until the 90s or so. And in fact, the first place, so all these thoughts are bubbling, but the word agent-based modeling doesn't exist yet. That's what's interesting. No one has used that phrase at this point. And no one has really thought of this as a revolutionary new idea. But John Miller, who is a social scientist, computational social scientist at Carnegie Mellon, and John Howland come together in 1991 to publish a paper on artificial adaptive agents in economic theory. As far as we know, this is the first use of the word agent and the way we use it in the phrase agent-based modeling, right? Where we had a computational agent who is called an agent making decisions in a complex system. I'm not saying that this is the first agent-based model. You can point back to things like the Schelling model, which comes in like the 1960s or 70s, and you can point to Robert Axelrod's work in Evolution of Cooperation in the early 80s and call that agent-based models. But none of those people had used the word agent to describe the entities in their models, right? It wasn't until this point, and I keep asking for somebody to prove me wrong on this, right? But I have yet to find someone who has. You could also point to the work in biology that was going on where they talk about individual-based modeling, right? But they don't use the word agent, and they were talking about individuals in a population system. You could argue this is all semantics, but I think it's kind of interesting to at least figure out where these words come from and where they first happened, right? I should say that almost all of these works, and this is one thing, and this is this guy here, were inspired by Herbert Simon. And in fact, I personally believe that almost all of complexity theory since about the 1990s has been trying to figure out what Herbert Simon was telling us 20 years before that, right, in the 1970s, right? If you want some books to read from and really get inspired, take a look at any of Herbert Simon's works, right? And they really lay out the groundwork for most of modern complex systems in interesting ways. And so Herbert Simon had mentioned the word bounded rationality very early on in those at times. Howland was also a member of a group of researchers at Michigan known as the BACH Group, right? The BACH Group was made up of Arthur Burks, Robert Axelrod, Michael Cohen, and John Howland, right? This group also inspired two prominent graduate students who continue to this day to work in the space, Melanie Mitchell and Stephanie Forrest, to continue to publish agent-based models. So there's a huge, now you can see in the early 90s, you start to see the development of an academic community interested in exploring the world of agent-based models and where they can possibly go. Working with this group, Howland actually developed something called the classifier system, which was an attempt to start to bring a language to adaptive agents, right? And this led to the idea of a world where Howland really wanted to build an agent-based model that would always be new. It would always create new things. The world of what he called never-ending novelty, right? And his argument was that evolution does this. We should be able to incorporate this into a computational simulation, right? And so he developed this model called the ECHO model, which is talked about in this book called Hidden Order. Actually, it was first described, I should mention, it was first, so there's a series of lectures that happen every year at the Santa Fe Institute called the Stanislaw Ulam Lectures, where they invited Nobel scientists to come and give, I think, 3 to 5 lectures, I can't remember the exact number, over a series of night to a public audience, right? Very hard thing to do, right? In a Santa Fe auditorium. And believe me, I've been to Santa Fe a lot of times, and the people in that audience for those lectures are an interesting group of people because Santa Fe attracts people from, your more normal, ordinary walks of life all the way to people who've decided that they need to be hermits in a desert, right? And so there's a very interesting mix who show up at that group. Anyways, Holland, survives this experience and writes a book about the experience called Hidden Order. So that's another thread. And I want to talk about a different thread in agent-based modeling that is very important, which is the work that was done by Seymour Papert and Logo, right? Because so far, a lot of what I've been talking about, I'll call the Michigan School of Agent-Based Modeling, because it comes out of the University of Michigan, essentially, most of the work in that space. Seymour Papert is at MIT. He co-founds the Artificial Intelligence Lab at MIT, right? And he starts to think about other concepts about how we can build computational modeling. So we're jumping back in time again. We're going back to the 1960s, right? He studied with a famous learning researcher known as Piaget in Switzerland before he came to the United States, right? And in the late 60s, he with Marvin Minsky, probably one of the most prominent AI researchers in history, puts together the AI lab at MIT. Him, together with some of his students, create the language called Logo in 1969. Logo is based upon the artificial intelligence language Lisp, but was designed to give children access to programming. As we mentioned, there's the turtle. Here's another picture of that turtle. This one might look more like a turtle. I don't know. Maybe less. Can squint. The turtle was developed post-Logo, so the language was developed first, but then they realized they needed something to kind of help students think. And so he uses this phrase that the turtle is a body syntonic object, which essentially means you can almost you can think about how you might embed yourself in the turtle, right? You can place yourself in the role of the turtle, right? And so it helps you to think better about the world. Without it, if you just have this abstract object on a screen, it's harder, he argued, to think about what it means for the turtle to do. The early turtles were mechanical and tethered to computer, but soon became virtual and visual. Logo was introduced to schools, millions of children participated in using it. The Logo turtle may have been the first actual computational agent, even though it wasn't called that, in widespread use, right? It's one way to think of it. By the way, there was a huge, at least in the United States, there was a huge kind of, everyone has to learn Logo at one point when I was growing up in my generation. So in 3rd grade, you were marched into a classroom of Apple IIe's, and someone taught you how to draw squares with the turtle, right? And that was like kind of forcing everyone to do that kind of thing. Partially because Apple gave all the schools a lot of money to spend on their computers, and then people had to figure out what to do with those computers, right? So that was what they went to. So NetLogo takes much of its syntax from Logo. It also borrowed, this Logo slogan exists, low threshold, high ceiling. The influence of Logo is not only in NetLogo, but you can see it in many other agent-based modeling languages, right? Many languages have this idea that you have this like physical object in a physical space and you're controlling its movement in that space as part of it. A lot of people kind of get upset with the idea. They're like, well, I don't have physical agents. I just have mental agents, right, that do processing, right? And then they're like, so I can't use NetLogo. I'm like, no, you could just ignore the physical space, right? Like, you don't have to use it. It's there just to help you with the visualization, right? So one of the cool things that NetLogo incorporates, or Logo incorporates, I want to briefly mention, is a function, right? And the expansion of a function. So a function in a programming language originally is just, give you an input, you give me an output, right? And that's all a function does, right? John McCarthy's work on Lisp in 1958 expanded the notion of function, building upon Alonzo Church's work on something called the lambda calculus in 1932. Here's the cool thing about that. He says, hey, why can't a function take another function as its input. Right? So in NetLogo, there's something known as an anonymous function, and that's exactly this idea. That I have a function, and I pass it an anonymous function, and it can then take that as an input, process data, and go out. So what might that look like? Well, an example, for instance, is something called map in the NetLogo language. Map takes a list and takes a function, and it maps that function onto that list. So it can, for instance, in the simplest case, it could take each element in the list and multiply it times 2, right? And give you another list out that is all those elements times 2. By the way, Lisp keeps the functions and data separate, right? NetLogo does too, right? You have different functions and different data. So you needed different addition operators for different data types, right? So then we have the idea of object-oriented programming that kind of arises from this stream of thought. So this guy, Alan Kay, who I had the pleasure of meeting at one of the talks I gave, he's a cool guy. He kind of really formulates object-oriented programming in this language called Smalltalk. And there, the language is that a function and its data belong together, right? And so they're kind of part of each other. And so therefore, you describe a function as how it operates on the data it's given. So now, you don't really need to worry about different addition functions, right? Because you just call the addition function that's attached to that piece of data, and it knows what that data is, and it runs the function on that data, right? By the way, Alan Kay is not arguably the first person to come up with object-oriented programming. There's some guys named Dahl and Nygaard who, I believe this is up in Scandinavia someplace, developed a language called Simula, which, interestingly enough, I think is kind of a new, interesting notion, created the idea to simulate actually building of ships, right? And how those ships might work. So actually, object-oriented programming originally was developed for simulation, right? Which is kind of cool that we're bringing it back now to agent-based modeling. I'm going to go for a couple more minutes. Okay. So what is the relationship between object-oriented programming and ABM? Well, agents are often instantiated essentially as objects. And NetLogo is not a full object-oriented language, right? I should say that real quick. But NetLogo does support the notion of breeds, which gives it a semi-object-oriented language. So you can create different breeds, and we'll talk about that this afternoon. And those breeds can each have the same function attached to them and can output different things as a result, right? So it has some limited object-oriented functionality. I think it's important to mention a couple of more strains of thought that kind of led to agent-based modeling. So a guy named Carl Hewitt at IBM developed the actor model of programming, which was formalized eventually by these guys, Bishop and Steiger. This model simplified the Smalltalk and Simula. It was influenced by Papworth's work on body syntonic reasoning at the same time, and Kay's work on object-oriented. So now everything comes together, right, like, in some ways. And the actor model is really cool. The actor model basically is agent-based modeling as a programming language, right? It basically says that actors, which are your objects, right, can only do a few things. They can send a message, they can receive a message, they can create other actors, and they can change messages that they have, right? If you think about that, like our diffusion of information model that we're building, that's essentially our diffusion of information model, right? In many ways, except we don't allow them to create other actors, but other than that, everything else is, right? Each actor has an address, and the only way to send a message to an actor is to know its address, right? So if you don't know its address, you can't send it a message. And each actor has only a limited number of addresses it can know, right? So as a result, in order to find out the address of an actor who's like 3 steps away, you would have to message people, right, and get the addresses back, right, as part of your messages. Which means that you have inherently the notion of local communication, which is very similar to agent-based modeling, right? Kind of cool. Moreover, actors were concurrent. So eventually, he wanted to actually use actors in things like telecom networks to actually build the logic behind a telecom network, a telecommunications network, right? And so as a result, these actors would actually be acting at the same time on different processors in different places, right? Eventually, all of this results in the modern O languages, C++, Objective-C, Cocoa, and the ABM platforms to a large extent. Actors influence this ABM in many ways, an emphasis on concurrent computation, local interactions, bounded interaction spaces, they're dynamic, and the notion of behaviors and properties of independent actors. One last strain of thought I really want to mention, which is parallelism. So parallelism comes along, developed by this guy named Danny Hillis, who has an interesting look on his face in this picture. And the idea of parallelism is that rather than having, now we take it for granted, almost all of these machines have more than one processor on them, right? But at the time, that wasn't the case. Machines had one processor at most, right? Danny actually liked the idea of having many, many processors. So he actually built machines that had thousands of processors, right? He used the framework known as the single instruction multiple data, and he founded thinking machines to commercialize this product. By the end of the 80s, there were several special programming languages such as Starless and C Star were developed for this machine. The CM2, the Connection Machine 2, had 65,000 processors in it. This is like 1989, right? Think about that. Most of ours only have 8 processors on them. Any idea why we don't have a 65,000 processor on our laptops? We could put them in there. Anyone know why we don't have one? Yeah, but we could put cheap ones. GPUs are a great example where we do have them on there. Why don't we use them for everyday computing? Yeah, our current code is not, but that we could write it. But what? So it's closest to this, right? It turns out it's really hard to write good parallel code, right? Computer programmers have a really hard time thinking about how to use 8 processors, let alone 65,000 processors to a large extent, right? And so a lot of it has to do with the fact that, quite frankly, we don't really know how to take advantage of 65,000 processors. There's a whole field of research now on GPUs that's essentially dedicated to exactly understanding that problem. And it turns out that for a lot of our simple applications for day-to-day, it wouldn't really help to have 65,000 processors, right? The 8 processors working at high speed is better than 130 processors or whatever, 160 processors working at slower speeds, right? So data was spread across the processors. One of the interesting things is document retrieval is really easy in this space, right? There are certain applications it works really well for, right? Like if I put a single document of 65,000 documents on 65,000 computers, it's simple for me to find the right document because I just send the same instruction to all of them. That one matches, it pulls it up. If I'm doing it on a sequential, I have to iterate through all 65,000, right? If I want to recognize an image, right, it's very easy for me to send part of the image to each of the processors, have it say yes or no, that's the same image, right? And then it passes me back that information. But there are things that are very difficult. Actually, the earliest form of NetLogo was a language called StarLogo. There was actually an agent-based modeling language written in this system, right? And so each agent could be on each processor. Couple other these are smaller stories, but I just want to mention them. There was some other work done by particle systems. So particle systems were a graphical system that was developed much like the Boyd's models, right? They weren't really intended to be computational systems. But in particle systems, you represent each point as a particle, each particle is a point, and then you simply applied physical forces to it, right? So you had gravity moving it down, some force moving it left or right. And it turns out that that worked really well for representing things like smoke or stars or light, right? But not so, but you know, and better than the tradition in graphics, which was to use surfaces to represent those spaces, right? So Reeves in 1983 defends these particle systems. They have emergent phenomenon. They look different. If you looked at an individual particle, it doesn't look like smoke or stars or anything, but you look at a group of them together, it does. That results in Boyd's, right? Building upon that, which we've already talked about in quite a bit. And so that's kind of the history, I would say, in a nutshell, of some of the main lines of thought that led to agent-based modeling. Now, there's a bunch of other stuff. There's individual-based modeling in biological systems. There's Bob Axelrod's work on evolution of cooperation. There's a bunch of other stories that we could tell here, right? But at least for NetLogo and for the agent-based modeling embodied by NetLogo, I think these are the main strains of thought that led to it. So with that, and it's almost one, I'm going to end by just showing you one of the particle systems, because I think, well, I'll show you the particle system and then I'll show you the game of life. So this is one of my favorites. So this is a fountain. Right? And it looks like a fountain, right? But all it is a series of blue dots being chucked up, right? And all it is each one of those is an agent that has a slight dynamic of how it moves up and down and left and right, and disappears off of it. And the same rule is applied to all of them at every time step, right, depending upon what's going. And if you want, you can play around with it. It looks a little better, actually, if you slow it down. They've gotten too fast, right? So there you go. There's the part of the fountain in slow motion. But, what's interesting is, how Stefan was talking about more is different yesterday, right? If I remove the number of particles, it stops looking like a fountain eventually. Is that a fountain now? I don't know. It's hard to say, right? And that just looks like some balls. It doesn't really look like much of anything, right? So I think it's interesting. It definitely is one of these cases where our experience is different, right, depending upon the number of things, not just the behavior of those things, right? So if you want to play around with this, I definitely encourage you to do so. You can also, so the thing about particle systems, I can start to do things like put a wind in, right? And change the direction fairly easily. Because all I'm doing is modifying the XY coordinates of each particle as it goes along. But I did want to make sure and to show you the game of life. So the game of life, I think, is one of the coolest simple models in existence, right? So I'm having it just generate a whole bunch of different random patterns right here. And as you can see, I start off a random system, but you already have some interesting things that occur. So for instance, in the game of life, if there's 4 cells next to each other and nothing else, they just stay forever, right? Because they all reinforce each other. If there's 3 cells, they become what's called a blinker and just move back and forth, right? And there are other structures that kind of move and change shape across the way. Like one of my favorite is called the glider, right? So, I draw cells. See if I can get this right off the top of my head. Oh, got one too many. I think that's it. Nope, that's not it. I did it wrong. Maybe it's that one. Yep, there you go. So the glider just moves. And always, every 5 time steps, it comes back to the exact same pattern. Just shift it down and to the right. Right? And it's kind of one of the coolest little things I've ever seen, right? For 5, for about 10 pieces of information, right? You can get this cool pattern, right? Anyways, that's kind of where I'll end it with the history of agent-based modeling. Are there any questions about that? Any thoughts? How many of these stories have you guys heard? Any of them? No? None? Okay, that's good. Some of the genetic algorithm stuff, maybe? What? Which one? You'd heard of Conway's Game of Life before? Yeah? Cellular Tom, I thought you'd heard of before. Anyone heard of particle systems before? No? Yeah. Or small talk. Anyone ever written in small talk? Or you'd heard of small talk? Okay. Have you written in small talk? Have you written anything in small talk? I actually did way back in the day, but that just shows how old I am. You learned Logo in school? Okay, awesome. All of you learned Logo? No, just a few of you. Okay. Okay, maybe it's just your school. Awesome, cool. Well, we're done with the theory now at this point. So in the afternoon, we'll come back and do a last tutorial. Yeah. What was that? You'd only heard of Game of Thrones? Well, because we know that all these systems are Turing complete, you could write the Game of Thrones in the Game of Life. That'd be really interesting, right? Maybe you could change the ending and actually make it decent. No. Cool. So yeah, Walensky was Seymour Papert's student, so he helped develop Star Logo. I should have mentioned that. I don't know why. I should put that on the slide. I feel bad. That's not on the slide. But yes, so Walensky was directly responsible for developing some of the applications in Star Logo, right? And then he graduated from MIT. His degree is in computer science, right? He graduates from MIT. Walensky is interesting. He actually spent a year as a poet. He had a National Endowment of the Arts scholarship to spend a year as a poet, and then he started teaching at Tufts University, right? And at Tufts University, there was actually a little bit of a falling out as they left, and essentially, one of Walensky's partners when he was at MIT was a guy named Mitch Resnick, and Mitch Resnick kept working on Star Logo and for some reason was able to retain the rights to that name, and Uri had to start over. So he developed something called Star Logo T, which was Star Logo Tufts. And then when he moved from Tufts to Northwestern, he kind of recreated Star Logo T as NetLogo. And it was a completely different version. It was not the same thing at all. And so that's where NetLogo comes from. And when he made that move, he also became jointly appointed between the School of Education and the School of Computer Science. So he actually works in both spaces. So if you look at NetLogo, you'll see a ton of models that are written for kids, right, essentially. Yeah. Does that kind of help explain a little bit more? Any other questions? So let's take a break till 2:30, and then we'll come back for the last tutorial.